Every single day we put our trust, sometimes even our lives, in the hands of bridges, cars, and tools, and we don't even think twice about it. But that trust, it's all built on a really fascinating science, the science of figuring out exactly how and when materials fail. And to do that, we have to start with a really basic question.
It's a simple question, right? But the answer is pretty much the foundation of all modern engineering. How can we be so sure that an airplane wing or a car axle is going to handle the stress of the real world? Well, the secret, it turns out, is to be a little bit destructive.
That's right. In super controlled lab settings, we push materials to their absolute limit until they break. Because by understanding failure, we learn how to design for success. Today, we're going to look at two of the classic ways we do this, the twist and the grind. Okay, first up is a test that's all about rotational force. I want you to think about anything that spins under pressure, like a drive shaft in your car or even the drill bit in your toolbox. This is how we find out just how tough they really are. So what this torsion test is really measuring is something called shear strength. See, we're not pulling it apart or squashing it. We are literally twisting it. And that's a unique kind of stress that tons of critical parts have to deal with, day in and day out. The whole process is actually pretty simple to picture. Imagine you're wringing out a soaking wet towel. You hold one end totally still, and you twist the other. That is exactly what this machine does, just with incredible precision, measuring every single degree of rotation and every ounce of force, until, pop, it breaks.
Okay, but here's where things get a little tricky. Unlike a simple test where you just pull something apart, the stress in a torsion test isn't spread out evenly. The material right at the very center of a solid rod, it's barely twisting at all. Meanwhile, the outer surface is taking the absolute full force of the twist.
And this is exactly why engineers sometimes use holo tubes for these tests. It's a clever trick. By getting rid of that, lazy material in the middle that isn't really doing much work, you get a much more even stress spread through the part of the material you actually want to test. It just gives you a clearer picture of its true strength under torsion. So why does all of this matter? Because these twisting forces are literally everywhere. The axle on your car, the main shaft in a jet engine, even a simple drill bit. They all live in a world of constant twisting. And the data from these tests is what keeps them from snapping right when you need them most. All right, so we've twisted our material until it finally broke, but the test is far from over. In fact, you could argue the most important part is just getting started, reading the story that the break itself tells us. And the break reveals one of two very different stories. A ductile material, that's something that can stretch and bend a bit, like steel, it'll fail in a clean, flat break, straight across. It just gives up along that main twisting line. But a brittle material, like, say, cast iron, tells a totally different story. It fails at this weird 45-degree angle, almost like a corkscrew. The reason is the maximum pulling force or tension in a twist actually happens at that 45-degree angle, and for a brittle material, that's its weakest point. And that really is the heart of it all. That final fracture, that broken surface, it's like a complete report card on how that material behaves. By looking at it, an engineer knows exactly what they can expect from it out in the real world. Now, let's shift gears. We're moving away from those big, catastrophic one-time breaks to a much slower, but just as destructive, enemy, wear. This is the constant, relentless grind that slowly destroys machines from the inside out. I mean, wear is responsible for an absolutely incredible amount of economic loss every single year. It's the reason engine parts fail, bearings seize up, and huge industrial equipment needs to be replaced all the time. So understanding it is absolutely critical if you want to build anything that lasts. So to study wear, scientists look at what they call a tribological system. It sounds super technical, I know, but just think about a bicycle chain. You've got your main material, the chain itself, and the counter material, the gear. Then you've got the stuff in between, like dirt or lubricant. You have the load, that's the force from you pedaling, and of course, you have the motion. If you change any one of those things, you completely change how quickly your chain wears out. So how does this material actually get worn away? Well, there are a bunch of different ways, but we're going to focus on two of the most common ones. One that's kind of like sticking, and another that's basically just scratching. Over on the left, we've got adhesive wear. Now this is wild. At a microscopic level, two metal surfaces sliding past each other can actually fuse together at their highest points in a tiny cold weld. As they keep moving, they just tear these little welds apart, ripping tiny chunks of material from one surface onto the other. On the right is abrasive wear, which is a lot easier to imagine. It's just a harder material, scratching, gouging, or plowing bits out of a softer one. Think of a single grain of sand inside your engine oil. That's a tiny abrasive particle causing a whole lot of damage.
And let me tell you, abrasive wear is public enemy #1 in heavy industry. Any machine that's designed to dig or crush or move rock and dirt is in a constant battle against it. The lifespan of these incredibly expensive parts is pretty much all about how well they can resist this constant grinding.
So we've twisted things till they've snapped, and we've ground them down till they've worn away. It all sounds purely destructive, doesn't it? But the goal is the absolute opposite. It's all about creation and safety. When you boil it all down, it's pretty simple. The torsion test gives us the data we need to design parts that can handle all that twisting without failing. The wear test gives us the knowledge to create surfaces that can withstand friction for thousands of hours. Two different tests, two different ways things can fail, but they share one common goal: durability.
And that's really the big takeaway here. Materials science isn't just about finding the strongest stuff out there. It's about deeply understanding a material's weaknesses, its failure points, and its limits, so that we can design things in a way that they never, ever reach them.
Which leaves us with a pretty fascinating question for the future, right? We're now creating materials that can heal themselves, that can change their shape, or even tell us when they're under stress. So how do we even begin to test the limits of materials that are designed to maybe not have any limits at all? It's a challenge that's going to define the next generation of engineering. Thanks so much for joining me.